In this lecture, we're going to take a much closer and more detailed look at what you should do when you're presented with a chemistry problem that you do not immediately know how to solve. In fact, if you're certain you know how to solve it, then in my view, it really isn't a problem. It's something more like an exercise. It's when you don't immediately know what to do that problem solving really begins. So we're going to be discussing how you should think about it, the kinds of processes and mental activities that you should be engaging in and utilizing. I really hope that you will try to do the things that I'm going to recommend. If there were some way I could demand it of you, I would, but since that isn't possible, all I can do is ask you to try doing the things recommended in this lecture. I hope and believe that they will prove to be pretty beneficial and useful. When you are presented with a problem, either in this series of lectures or in your chemistry class, the absolute positive single most important thing that you can do is to work at understanding what the units stated in the problem really represent. Just as you really understood what was meant by the terms 3,000 students and 30 students per room, you must work at really understanding, really deeply understanding what is meant by terms like 5.33 grams or 83.2 grams per mole or whatever else might be given in the problem. You literally should stop and try to visualize these things in your mind. Your goal is to make each of the quantities presented in a problem as meaningful to you as 3,000 students and 30 students per room. And, as we said in the last lecture, the numbers and their units are generally going to be of two types. Some are going to be what we've called amounts, and others are going to be what we've called a this per that. 3,000 students was an amount. 30 students per room was a this per that. Let's take a closer, more detailed look at the this per that idea, because this is what gives students in chemistry the most difficulty and leads some of them to have limited success. Suppose I give you a quantity like 60 miles per hour, and I ask you what that really means. Think about that for a moment. What does this really tell us? Now, you might say something like, well, that tells me how fast you were driving. Well, okay. Well, let's be more specific. What exactly is it telling you? Quantitatively, a term like this is telling you, listen carefully, how far you will drive in 1 hour. Start over here, drive for 1 hour, and you will have traveled a distance of 60 miles. It tells you how many of these you have, 60 miles, for one of these 1 hour. What does a term like 25 miles per gallon tell you? You've probably used this term many times yourself. Perhaps you've bragged to your friends that your new car gets over 40 miles per gallon of gas, while his car only gets 25 miles per gallon of gas. Now, what does that mean? Think about that. Well, what it means is it tells you how many miles you can drive your car on 1 gallon of gas. How many of these miles you have for one of these gallons. What about a quantity like $4 per pound? What does it mean? Candy costs $4 per pound. You've probably used that term thousands of times in your life, but what does it really mean? What it is telling me is how many dollars it will take to buy 1 pound of candy. Quotients like these tell me how many of the numerator it takes for one of the denominator. Now, I suspect that many of you are thinking, all right, already, this is easy. I understand this perfectly. There's no need to explain it any further. And you probably do understand it. Students typically have little difficulty explaining what is represented by quotients like these. They've used similar terms often in their life, so they generally have a good intuitive understanding of what they really mean. But here is the one critical example that is not so obvious. What does the term 1 hour per 60 miles tell you? Think about that for a moment and pause the DVD if necessary. What does that tell you? Many students, when presented with a quantity like this, will say, that tells me how long it takes to drive 60 miles, 1 hour. And that isn't incorrect. But, and this is the major but, that is not the way you should think about this. But it probably is the way you do think about it. You probably interpret this as telling you how long it takes to drive 60 miles. I mean, after all, there's a number 60 in the denominator. But that's not the most useful way to interpret that quotient. Here is how you should think about it. This is actually one of the keys to being successful at solving high school chemistry problems. This tells me how long it takes to drive 1 mile. 1 mile? Yeah, it tells me how long it takes to drive 1 mile. No, it doesn't. It tells me how long it takes to drive 60 miles. Well, I mean, okay, I guess it does. I mean, there is the number 60 in the denominator. But that's not the way I want you to think about these kinds of quotients. Forget that there's a number in the denominator in this example, 60. Instead, anytime you see a quotient like this, you must mentally visualize the denominator as being 1. This tells me how long it takes to drive 1 mile. Hey, I mean, get out your calculator if you like. I mean, do the arithmetic and you'll come up with a number 0.0167. It takes 0.0167 hours to drive 1 mile. Now you might be thinking, it's all the same thing. Mathematically, yes, of course it is. But I want you to get into the habit of basically ignoring the number in the denominator in these kinds of quotients. Instead, just look at the units, hours over miles. And in your mind, immediately think, oh, this particular this per that tells me how many hours it will take to drive 1 mile. You will become much better at solving chemistry problems if you develop the ability to look at a quantity like 1 hour over 60 miles, but in your mind, you see an expression that tells you how long it takes to drive 1 mile. Again, you basically ignore the fact that there is a big number in the denominator. You focus your attention on the fact that units of hours per mile tells you how long it takes to drive 1 mile. And you're going to see shortly why it's important to think about it that way. So let's try a few for practice again. Pause the DVD if necessary. What is meant by the quotient 1 gallon over 25 miles? This tells me how many gallons of gas it's going to take to drive 1 mile. Now you might object, saying, but it doesn't take a whole gallon of gas to only drive 1 mile. Yeah, so? No one ever said that the answer couldn't be a fraction. Do the arithmetic if you like. I mean, I guess it comes out to be something like 0.04 gallons per mile. So what? The expression is telling me how many gallons of gas, in this case less than 1, it takes to drive 1 mile. Cover up the numbers. Forget about the numbers. Gallons per mile tells me how many gallons of gas, and it might be a fraction of a gallon, how many gallons of gas it takes to drive 1 mile. In this case, it would take less than a gallon, considerably less. What does 1 pound over $4 tell me? What this tells me is how many pounds of candy I can buy for $1. Now, you probably can see that I can't buy a whole pound of candy with $1. I mean, if I walk into the store and hand the lady $1, she's not going to give me a pound. She's going to give me 1/4 of a pound. But that doesn't matter. Anytime you see a this per that, listen carefully. Anytime you have a this per that, it's telling you how many you have of whatever you've written in the numerator for 1 of whatever you've written in the denominator. That sounds like a pretty simple idea, but it's really kind of important that you understand that. And we're going to come back to this idea time and time again. A number like 30 students per room is easy to see. I mean, it tells me the number of students in one room. 60 miles per hour is easy to see. It tells me how many miles I can drive in 1 hour. But when the denominator isn't 1, it becomes a bit trickier. But even if there is a number in the denominator, like 25 or 60, you must not focus on that number, but must remember that the expression is really telling you how many of the numerator you have for one of the denominator, not 25 or 60. So what exactly am I asking you to do? When you're presented with a problem, either here or in your class, here's what you do. I think this may be a rather critical moment. If you don't want to do this, I mean, if you prefer, if you don't care to do this, if you prefer to just keep doing what you've been doing or might prefer to do, well, you can't get the maximum benefit from this series of lectures. But if you are willing to keep trying, even if at times it seems like a lot of work, I've even had students say things like, "This is good, but my brain hurts from all this thinking." But if you are willing, then there is a good chance that you will do much better in high school chemistry, hopefully becoming an outstanding student. There's even a chance that you might even become the class guru, with other students coming to you to learn how to understand what is going on. Here is what you must do when presented with a problem. Read the problem several times. First quickly, to kind of get the overall picture of the problem, then slowly. Now I'm going to add a little qualifier here. If the problem is so trivial to you that you know exactly what to do with it, I mean, if I say 3,000 students and 30 students per room and you say, well, I know how to do that, then you don't have to go through all this. I'm assuming that the answer is not immediately obvious to you. So when you're presented with a problem that is not immediately obvious, you do this. Read the problem several times, first quickly and then slowly, stopping, thinking, and visualizing as you go along. Literally, close your eyes and try to picture what you see in that problem. Picture the students, picture the rooms, picture the students per room. Picture the grams, picture the moles, picture the grams per mole. Visualize that problem. It often helps to draw a picture of the quantities represented in the problem. And as we go along, I'll show you what I mean by pictures of chemical quantities. Always attach proper units to all numbers and think about what these numbers represent. Always attach the proper units. Many students, I guess it's just carelessness, hesitate to do this. They write down 8.33 and 45.7, but don't say 8.33 grams and 45.7 grams per mole. They just write down 8.33 and 45.7, and then they wonder, why are they having difficulty solving this problem? Remember my $1 million offer? If you can't write down the units that go with the numbers, then how are you supposed to know what they represent? And if you don't know what they represent, then how can you possibly know what to do with the numbers? Always, always, always attach the proper units to numbers and then think about what these units really represent. Now, if you do all these things, if you read the problem, if you think about it, think about the numbers, attach the proper units, etc., hopefully what's going to happen is that it will immediately, or at least eventually, become clear to you how these numbers have to go together to obtain the answer requested, just as it was very clear to you in the students and rooms problem. If you can successfully complete these tasks, what's going to happen as these lectures progress is that chemistry problems are going to look more and more like students and rooms problems. Furthermore, if you still have difficulty, there are some other techniques that I will suggest that can help you along the way. For example, when you finish a problem, you can often look to see if